Assalamu alaikum wa rahmatullahi wa barakatuh. In this week's experiment, we will revisit the simple pendulum again. And I will not dive into the theory in a great details for two reasons. And the first reason is because that you are just getting started, I believe, into learning more about the forces. And I think the simplest picture that we can draw for the simple pendulum is using forces. The second reason is that in chapter 15, the last chapter of this course, you will have the opportunity to learn more and to meet the simple pendulum with a more detailed treatment. In any case, again, this experiment will not need, or rather will not require a great or a complicated theory. Simply, again, we have a rope connected to a ceiling, and connected to that rope, we have a mass. We call it the bob. This bob is displayed from the vertical by an angle theta. And the gravity works on this bob by a certain magnitude, and it has two components, a tangential component and a normal component, as you will know as you go to further in the course. In any case, there is an important parameter that we'd like to study or investigate in this pendulum. That is the period, and the period is defined as the time required for the bob to complete one oscillation. So start from here, for example, go all the way to the other side and go back. When it goes back, this time is the period. And in this case, we'll use an important approximation. As you can see, the tangential component has a sine theta factor. And we will approximate this sine theta by theta. This will make our lives much more easier, and we can write the period using this equation thanks to this approximation. Now we learned this about this period and this relation in the first experiment. The period is given by 2 pi times the square root of L divided by G. So the period depends on the length of the rope, and it depends also inversely on the gravitational constant. But as you can see, we do not see any masses here, so the period is independent of the mass. And also we do not see any angles, so the amplitude of the motion that will not affect the period in this case. Okay, so let's get started. We have three parts in this experiment. The first part, we would like to determine the value of the gravitational acceleration g for a certain planet x. Okay, and in the second part, we would like to find the relation between the period and the variable mass. And spoilers alert, we know that the mass will not affect the period, but we will verify this independence in this experiment. And in the third part, we'd like to know the relation between the period and the length. And we also know this relation, but we'd like to apply our skills in data analysis and use Excel to verify this relation and investigate it more. So let's get started by clicking on the simulation link. Again, click start. And we will work in the lab environment. Okay, so as you can see, the simulation has many features. You can move the pendulum or the bob by clicking on it and dragging. And as you can see in the top, you can see the angle that the pendulum makes with the bob makes with the vertical. Okay, we can control that. What's also important, for example, suppose you let it go, you can click pause from here, and you can change the length of the rope from this option. You can change the mass. Again, there are many features that we will get to know if it's matter to us in this experiment, and I'll leave you to play with the rest if you are interested. Note that we have important features in this simulation. This line represents the beginning line, the maximum in this direction, and this line represents the maximum in the other direction. And of course, as you know, or you should know by physical intuition that there is a symmetry in this case, but this doesn't matter. But make sure that when we find the period, that you follow the motion of the bob when it crosses one of these lines. So choose your reference. You can, for example, let the bob go from this position or from this position or from any other position that you want. But I let it go usually from the right hand side. So let's get back to the manual and read it and follow the instructions that we are given. So in this part of the experiment, we will be using simulation to determine the value of the gravitational acceleration for planet X, as we said, using the time period and length of simple pendulum using equation 6. What's the equation 6? It is this equation. Okay, so from the right menu, choose the gravity for planet X and set the length to 0.7 and the mass to 1 kilogram. So from here, click on planet X and set the length to 0.7 and the mass to 1 kilogram. Okay, now pull the bob to the right side by 5 degrees and record the time for 5 oscillations. Okay, so pull the bob to 5 degrees and we record the time using the stopwatch. As I said, we can use the you can use the period timer, but we'd like to give you a feeling of a real experiment. So we'll use the stopwatch. Okay, and it says record the time for 5 oscillations. So click on start and click start 1, and I'll count whenever this bob matches the line, this blue reference line. Okay, 2, 3, 4, 5. Okay, so 6.98 seconds. Okay, 6.98 seconds. As you can see, I paused. So just to verify, we'll do it for a second time and for a third time for different angles. Now we'll do it again for 10 degrees. Okay, reset your counter, click start, and it will not start unless you press go. 1, 2, 3, 4, 5. Okay, as you can see, it actually passed the reference line, but it's okay. This is an experimental error, but it's expected in this case. Okay, so it's 7.08. 7.08. Now we'll do it again for a third time for 15 degrees. Reset your counter. Click start. 1, 2, 3, 4, 5. Okay, 6.95. 6.95. Okay, now this is the time for 5 oscillations. To get the time for a single period, you'll divide this number by 5. Okay, and then you will find the gravitational acceleration. You can do this manually using the equation 6, but I'll do it in Excel. So let's move to Excel. Copy this, go to Excel, paste. Now if you notice in equation 6 we use the period square. So I'll make another column for the period square. Okay, and as we said, to get the period, divide this by 5. So apply this to other cells. Move your cursor till you find this small cross, this small block cross, and then click and drag. Okay, and to find the period square, simply click equals this cell squared, and again apply it to the rest. And just a piece of advice, if you would like to have less number of decimal places, just to make it cleaner, you can select this data and click on this in this option. Okay, let's keep it to 3 decimal places. This will be good. Okay, now we'd like to find the gravitational acceleration for this planet X in meters per second square. And as if you remember the equation, it's equals to 4. Do not forget the multiplication sign, 4 pi squared times the length divided by the period squared. Okay, be careful with your selection. Now you can also apply this to the other measurements, and just to make it cleaner again, reduce the number of decimal places to 3. Okay, now we are asked to find also the average value of g. You can do it manually by summing the 3 values and dividing by 3, or in Excel you can find the average. Okay, so in the last part you will find the percent error between the experimental value and the estimated value. The experimental value is the average value that you obtained, and the estimated value is this value given in the question. And let's suppose, and as given, it's 15. Now you will answer these questions in blue again in the data analysis, and these in green in the data section. And let's do that just to show you how the report template works. So copy this information for the length and the mass. And I know that the mass does not matter in our case, but let's pretend that maybe it matters. Let's pretend that we do not know. Okay, so copy this information, copy this table into the data section again. Okay, and we'll get the information about the period from the Excel, or as I said, you can get it manually. Okay, nice. Okay, now as for the these observations, also copy them. Let's in fact copy all of the required questions. Copy, go to the data analysis. In this part, as you can see, in the data, part A, determine the value of gravitational acceleration for planet X, and the data analysis in part A for the same section. Paste. Now we obtain this information in Excel. So copy, paste. That's a simple life. Okay, let's copy this value also, paste here, and let's also record the equation that we used to determine the gravitational constant. So copy this equation also and paste it in the data analysis section in the first part. Okay, notice that we do not want to have a letter for this part, for this table, so just to make also our work and our report neat and clean. Okay, and as for the last sentence, remove the question statement, remove F estimated and say the estimated, and remove this also. Let's make it all in blue, and choose your favorite color. It's okay with me. Okay, so let's make it all in blue. Nice. So after calculating the percent difference, also write it down here, and this completes the part A of our experiment. Okay, let's do part B. Now in part B it says again we want to find the relation between the period and between the mass. So let's read the instruction. In this part, you will investigate whether the time period of a simple pendulum is independent of the mass of the bob. You will be measuring the time period of oscillation while changing the mass of the bob and keeping the length of the pendulum fixed. You can vary the mass of the bob M from the right side menu. We know that. And the procedure is given below in greater detail. So choose gravity of Earth from the right menu. Okay, so let's get back to Earth. And set the length to 0.7 and the mass to 0.4 and displace the bob by 10 degrees. 0.7, 0.4 and displace the mass by 10 degrees. Okay, and measure and record the time for 5 oscillations. Okay, so let's click start, and it will not start unless we press start from here. 1, 2, 3, 4, 5. Okay, it's 8.36. So 8.36. We'll do it again just for verification. Okay. 1, 2, 3, 4, 5. Okay, 8.37. Okay, very close. Now you will find the average. Add these two and divide by 2. As you can see, it will be something like 8.365, and I'll just write it down as 3.7. Okay, and now to find the period, divide this number by 5, and in the end what you'll need to do is you need to find the average value of the period. So you'll do this. This is the first trial. You'll change the mass to 0.5 from here to 0.5, and again do 5 oscillations twice. Okay, and find the average, find the period from the average, and do it again for 0.6. In the end, you will find the average value from these values. Okay, so add these 3 and divide by 3, or you can move to Excel and do it, but it would be an overkill. Now you will copy this table of data along with this information in the data section, and you will answer this question in the data analysis section. Okay, now let's move to the third part. And again, you should read this information or the instructions carefully. But I think by now you are already familiar with what you should do. Now choose the gravity of Earth, already set. Set the length to 0.7 and the mass to 0.4. Already set. Displace the bob from equilibrium position by 10 degrees. Measure and record the time for 5 oscillations, and do this in the table. Now, in this part, you hopefully obtained that the period is independent of the mass, and in this whole table, we did the measurement for the period when the length was 0.7. So we can copy the information of this trial and paste it into this table for the first trial, because we already did it in the previous part. So let's start by 0.8 instead. So going back to our simulation, let's increase the length to 0.8. Okay, 1 2 3 4 5. تمام. 8.94. So here it's 8.94. Let's do it again. 1 2 3 4 5. Again 8.94. How accurate. Okay, so the average would be basically the same, 8.94, and we obtained these values from the previous part. Let's just paste. Nice. Okay, and then you will do it for a third time by increasing the length to 0.9. Okay, so increase the length. Oh, the length here was 0.79. Be careful. It should be 0.8. Okay, and in the third trial, it should be 0.9. But I'll take that. Suppose I do not know. In the end, I'll get an experimental error. But let's continue. Suppose I continued for 0.9 again. Then I'll copy this table. By the way, let's do it. Let's do it for 0.9. Why not? It's only a matter of 10 seconds. Okay. So it is in 10 degrees. Yeah. Start. 1, 2, 3, 4, 5. Okay. 9.51. 9.51. Let's do it again. And make sure that you count whenever the bob crosses the reference line. In my case, my reference line is this line, okay, on the right hand side. You can choose either one. You can choose this one or that one. Okay, 1, 2, 3, 4, 5. Okay, 9.50. Okay, it will be 9.51. Okay, it should be 505, but let's approximate it to 9.51. Now let's move to Excel, because now it asks us to find the plot of t versus square root of L, and to answer the rest of the questions. So let's go to Excel, copy this table. Let's have a clean sheet. You can use the same sheet, but it's up to you. Paste. Now to get the period, as we said, divide this time by 5, and apply the same to the rest of the values. And to find the square root of length, click equals sqrt, select this, select the length, and enter, and apply the same function to the rest of the cells. And also, to make it cleaner, reduce the number of decimal places to 3. Alright, we want to plot the t versus square root of L. So suppose we selected these two columns and clicked insert, scatter plot. Okay. As you can see here, the maximum value in this x-axis is 1.95. Now we want to plot t versus square root of L. So the t should be here, and square root of L should be here. So what we should do instead, right-click on this plot, select data, select the x values to be the square root of L, enter, and the y values to be the period. Okay, then click OK. As you can see, now we get t versus square root of L. And let's do not forget to change the layout. The axis title is t in seconds, and square root of L in square root of meters. And in the title, let's write down t T versus square root of L. Okay, we can also remove the legend, we do not need it here. Now right click on the data point, add trend line, this is important. Okay, click linear and click display equation on chart. Nice. Okay, so let's back to Excel and see what we are asked to do. Make a plot. Is it a straight line? Mine is a straight line because all three data points lie on the same line. Now apply linear fit, we did. Write your linear equation. It's displayed on the plot. That's fine. You can write it down if you like. What's the value of the slope? What does it represent? Now the value of the slope is also given here. It's 2.0346. And what does it represent? You should answer. Determine the value of g from the slope using equation 5. Where is equation 5? This is equation 5. And as we learned from the graphing experiment, I hope that you can get the g value from the slope. Okay, by linearizing this equation, write it in terms of y equals mx plus b, find the slope, and use it to find the g. Okay, now after determining the value of g from the slope, you will use the experimental value and compare it with the actual value, the standard value of g, and calculate the percent error. Now then answer the final question: does your data support the statement that the period depends on the square root of the length? Explain. You will answer these questions in blue in the data analysis section in your reports. Okay, here in part C, time period for fixed mass and variable length. Okay, and you will copy this table into the data section. And the plot in Excel, it's important, make a plot, copy this plot into the data analysis section. Okay, so copy this one to the data analysis section along with the other information that are required. For example, the equations, the slope, what does the slope represent, and etc. So answer all these equations into part C. Now the last part, the optional part, we are required to verify the relation or the approximation that we used, that sine theta is approximately theta. Okay, compute the percent difference between theta and sine theta for theta equals 10 degrees, and you must convert theta to radians for this comparison. Let me show you what does that mean. So in a new sheet, let's write down theta in degrees, and to expand the cell, double click on this boundary. Now let's start with 5 degrees, for example. 10, 15, 20, 30, 40, 50, etc. This is theta in degrees, and for the sake of comparison we need theta in radians. How can we do that? Simply do the conversion between degrees and radians. This is the angle in degrees multiplied by, what should we multiply by? Pi divided by 180. Okay, this should give us the angle in radians, and apply the same to the rest. So now we have theta in radians. Again, let's decrease the number of decimal places. Now we want to find sine theta. Sine theta again equals sine, and by default the sine function in Excel uses the radian measure. Okay, so sine theta And you can also apply the same for the rest of the angles. Now the percent error is equal to absolute value of the angle in radians minus the sine theta, the actual value, divided by the actual value multiplied by 100. Okay, and let's see the percent error. Now what does that mean? As you can see, this is the error in percent. So when the angle is small, like 5 or 10, we can see the percent error is very small, less than 1%. And when we use 15 degrees, the error is approximately 1%. As the angle increases, so the angle of the pendulum, as it increases, this approximation that sine theta is equal to theta is no longer valid. But as you can see, for small angles, it is very well it's very well applicable in our case. Now you should do this. You should do this table in Excel and do it. If you like to do the optional part and comment on the approximation that is used. And finally, do not forget to write down the conclusion. And by the way, the exercise that is optional is the last part in the report in the data analysis section.